Most people want a clean, fair and sustainable world, and it is frustrating that's not happening sooner. Political indifference or vested interests do contribute to this, but there's also a host of technical problems that have to be solved before we can reach this green future. We can't overhaul the entire world without overcoming some obstacles along the way. My name is Cormac O'Malley. I'm an electrical engineering PhD student with a research focus on low carbon power system operation. And I want to delve into these problems with you and hear from experts about the solutions that research can offer.
From the Integrated Development of Low Carbon Energy Systems programme at Imperial College London, this is Low Carbon Conversations, a podcast on the challenges of building a decarbonised energy system and the research that's helping us to overcome them. This podcast is supported by Energy Futures Lab, Imperial's Energy Institute. For more information, visit imperial.ac.uk/Energy Futures Lab.
In this episode, we can go a long way towards full decarbonisation by electrifying most things, like passenger cars and some heating. But there are some things like aviation and heavy industry which just aren't suited to electrification. But net zero means zero, and mostly decarbonising isn't good enough. So is there some other clean energy vector we can utilise? Many people think that clean energy vector is hydrogen, which can support electricity in reaching true zero emissions. But what is hydrogen and how do you use it for transporting energy? To explain these and other hydrogen-related queries, I spoke to Nixon Sunny, a research assistant in the Centre for Environmental Policy and a final year PhD student in the Chemical Engineering Department at Imperial. He also works part-time for the Hydrogen Economy team at the Department for Business, Energy and Industrial Strategy and was the lead model developer within the EU Horizon 2020 project called Elegancy. I really enjoyed our conversation and I found that Nixon did a balanced and considerate job of demystifying what hydrogen's role might be in our green future. I began our conversation by asking him to give some context on the current role of hydrogen in our energy systems and how that outlook's likely to change going forwards.
Right now, we use around 80 megatons worth of hydrogen across the world, primarily for industrial use. Around half of that is being used for ammonia production, where hydrogen is used as the main feedstock, and around the remaining half of that really goes towards oil refining in various hydro desulfurization and various other operations where hydrogen is a key substance. So we really don't use hydrogen for many other uses other than these industrial use today. But moving forward, we have various different stakeholders such as the Hydrogen Council and Statista who essentially envisage a role for hydrogen, which essentially travels much beyond what we see in operation today. And what that essentially means is that hydrogen might be deployed in applications such as transportation, power, heating, industry, and so on, with an expected 7 or 8-fold increase in the global hydrogen demand by 2050. And if you look at the scenarios that the Committee on Climate Change has put forward in the UK, you'll find that essentially within the 6th carbon budget that was published very recently, we see a role for hydrogen of around 90 terawatt hours worth of deployment by 2035 at very low, essentially low carbon hydrogen production at scale. And what that essentially means is that we will be ramping up our hydrogen production by a factor of 4 and making it low carbon at the same time. So there's essential value in analyzing the concept of hydrogen deployment across the energy system, given that a large number of stakeholders have essentially outlined that it could be deployed for so many usage at such a large scale.
You mentioned things to do with ramping up production and green production, and we're going to get into the meat of what those mean later on in the podcast. But I think to start with, I'd like to really just clarify what we're talking about when we're talking about hydrogen. It's obviously an element, it's a gas, but I think it's slightly unfamiliar how you actually get energy out of it and what sort of substance it's like. Would you say it's fair to just to think of it literally like methane? You burn it and you get heat, but instead of emitting CO2 and other sort of particulates, the only byproduct is water. Is it, in one's head, is that a fair way to think about it?
Sure. So I think fundamentally what's quite important to recognize is that hydrogen is a chemical energy vector, and that makes it slightly different to other low carbon energy vectors such as electricity. But in a simple term, you can view it much like you would do with conventional fuels such as methane. But I guess what's interesting is that hydrogen can be essentially converted in its physical form for a range of different applications. And that's what really makes it quite interesting to analyze in the context of transportation, for example, with aviation, where you could use liquefied hydrogen, or with essentially, gaseous hydrogen, where you pipe it into industries for decarbonizing heat, etc. The most important thing to understand for hydrogen is that in the vast majority of its uses, you basically generate no byproduct emissions other than essential production of water. So that makes it quite useful towards our goal of meeting carbon neutrality by 2050. And now then it's just a matter of question as to whether it's most suited to be used in a particular application or not.
Right. So you briefly touched on it when I asked you about where hydrogen is today. I think it's useful to begin our conversation about where it is in the future by talking about this high level concept of high levels of electrification supported by hydrogen infrastructure. Because I think this is an interesting idea. Is that electrification can take us a long way, but there are certain instances and certain times even where the cost of becoming fully decarbonized with only electricity becomes prohibitive. And that's why we need this second option, if you will. Maybe we could begin our conversation by talking about that.
Indeed. I think what's quite interesting to outline before we get into this discussion, it would be that in a carbon neutral scenario in the future, you could see various different roles emerging for electricity, hydrogen, and biofuels. And depending on your country or your region of interest and the type of resources that you have to hand, you may see different roles for each one of these energy vectors. And what's really important here is that, but in the context of electrification, we have mature electricity grids across different countries in the world, whereas we don't necessarily have a significant usage for biofuels and hydrogen across the energy system like we do with electricity, or with natural gas, for that example. And what's important is that moving towards a carbon neutral scenario, we're going to have to see an increase in the uptake of low carbon or zero carbon energy vectors. And electrification is particularly important here because we have found that decarbonizing electricity has been a comparatively easier task compared to the decarbonization of other sectors. And that's mainly because of the low cost of renewables and its large-scale uptake over the past few years. But when we start thinking quite seriously about decarbonization of aviation, industry, heating, for example, we start to see quite significant challenges posed to the electricity grid. And to take heating as an example, we see quite significant variability in the use profiles for heat across homes and commercial establishments over the course of a yearly time frame. And we need to have the electricity grid to be essentially set up in a way so as to be able to respond to that in a highly flexible manner to ensure that we get our heat when we most need it. And at the moment, that essentially will require us to install significant amounts of storage or have significant amounts of essential backup generation capacity if we wanted to completely electrify the use of heat. And hydrogen is particularly useful in this context because you could use it as a complementary energy vector, in addition to electrification, to essentially be able to operate a mix of solutions to be able to meet our highly variable demand for heat, especially during winter, for that example. And in other sectors of the economy, you can see that the challenges for electrification are much higher. Aviation, where essentially there are few alternative technologies other than synthetic fuels or, say, liquefied hydrogen, we can start to appreciate the value that having a portfolio of energy vectors might offer in helping us meet our targets.
Lovely. And I'm really looking forward to cracking some of those open with you and really exploring where hydrogen might play a part in the decarbonisation of these different sectors. But I think before that, it's important to go over the core production and transportation systems of hydrogen, because you mentioned that when you burn it, you get energy and water. So at the point of burning or the point of combustion, it's carbon neutral. But that's only relevant if when we produce the hydrogen in the first place, we're not emitting lots of CO2, because in that case, we're just shifting where the CO2 is produced. Yeah, I think the first thing to talk about is, how is hydrogen produced?
That's a really good question, Mac. So to outline the type of production methods for hydrogen would actually require us to go through another podcast entirely. So I'll give you a very quick overview. Quite interesting in when comparing different low carbon technologies or different production schemes for hydrogen, is that you'll find that they're hugely numerous. They can essentially comprise various different feedstocks such as methane, biomass. You could even combine various different types of electricity sources to be able to produce hydrogen. Globally, currently, the bulk of hydrogen production is mainly used as fossil fuels. So essentially, you have roughly half of your global hydrogen supply coming from natural gas reforming, and then the remainder of hydrogen production essentially coming from either oil reforming or essentially coal gasification. And then a small portion of the global supply presently is made up of water electrolysis.
Okay, so just to interrupt there, reformation is effectively, fossil fuels are hydrocarbons, and the hydro is hydrogen. So that's just some process where you're taking out the hydrogen from the hydrocarbon, and then I guess you would be the carbon from the hydrocarbon is emitted as CO2. So that's the current way it's done, but that in itself is polluting. Is that correct?
Absolutely. Yes, exactly. So currently we essentially use steam with essentially reforming technologies where hydrocarbons are used, and the carbon in that hydrocarbon is then essentially emitted directly to the atmosphere. And we know that going down this pathway is wholly incompatible with our vision for net zero by 2050. So we need to come up with ways in which we can make the production of hydrogen either very low carbon or net zero by that time frame. And there are a number of candidate technologies that we can use. So the methane reforming technologies or hydrocarbon technologies can firstly be combined with carbon abatement solutions such as carbon capture and storage, where you have very high capture rates for the CO2 removal, which essentially allow you to produce the hydrogen while drastically reducing or even completely eliminating the CO2 emissions that are released in that process. So that then essentially means that you will have to then figure out a way to store that carbon, but it won't be released directly into the atmosphere. And, that essentially allows you to operate that process very sustainably. Alternatively, you could use essentially water splitting or water electrolysis, which uses renewable power, which then allows you to essentially take in renewable electricity, which can then be used to split water electrochemically into hydrogen and oxygen, where then the hydrogen can be used for various different applications. And I guess what's important to indicate here is that if you derive your energy from renewable electricity, you will essentially see very low emissions attached to the production of hydrogen when you look at upstream emissions. Whereas with other production schemes, such as natural gas reforming, you'll have to start to worry about the upstream emissions associated with the supply of natural gas. And that becomes particularly important when you start looking at carbon accounting in net zero. But in addition to these processes, you can also produce it using biomass, where you could reform or gasify biomass to create hydrogen. That's at a much more pre-commercial stage at the moment, and it's undergoing quite a lot of research. And there are various different ways you can develop those technologies to operate at scale.
So pre-commercial sounds like a sort of a synonym for very expensive. Yeah, so you talk about this electrolysis, which I understand is effectively you run a current through water and you split it into its constituent parts, which are oxygen and hydrogen. Is this at a what you'd call a pre-commercial stage when compared to the reforming, which is already widely deployed?
That's a really interesting question. So I'd like to bring a historical perspective into answering that question, if I may. So water electrolysis was actually invented in the laboratory scale around 1789. So it's actually developed much earlier than steam methane reforming, which was essentially undergoing research in the 1910s and 1920s. And so we see quite a significant time frame before development for water electrolysis. But the fact that hydrocarbons were incredibly cheap has meant that steam methane reforming, although quite recent in historical terms, has matured into a position where it is now the global dominant supply of hydrogen. And presently, the market for water electrolysis and the supply for water electrolysis is fairly low, mainly because there hasn't been a business model or a driver for its deployment. So relative to steam methane reforming, it hasn't been deployed to the same scale where we would actually sort of see quite significant cost reductions. But it has significant potential to scale up and have essentially reduce its cost of supply.
I like that, taking the historical approach, but I guess it's not sort of net time that people have put into technology. Not net time that the technology has been around. It's sort of net hours that people have put into researching it and improving it that's important.
Absolutely.
So we have this technology which is electricity in, hydrogen out, and to me this is beginning to move into some of the districts where some of the areas where we can start to see where hydrogen might be useful. So in a future where we have decarbonized our electricity, it's likely to involve very high penetrations of variable renewable generation like solar or wind. And the problem with one of the main problems with integrating these technologies is the fact that you have to keep demand and generation balanced, electricity demand and electricity generation balanced at all times, which is hard to do if the wind is changing a lot and the solar is changing a lot and you can't predict it. And here we seem to be presented with quite an obvious opportunity where if our process uses electricity to produce hydrogen, we can turn it up when we have a lot of wind, and then turn it down again when it goes the other way, and maybe even burn the hydrogen or use the hydrogen in some way to support the low wind periods. Is this an area that's of particular interest? And is this something that people are talking about?
Definitely. Balancing the grid is a key concern moving forward into the future, especially for the reasons that you mentioned. With a high degree of renewable penetration, you're likely to see an increasing need for stable generation that can essentially back up the renewables at times of short supply or at times when the wind doesn't blow or the sun doesn't shine. So you're going to sort of have quite a lot of support and reinforcement to the electricity grid in order to be able to deal that. And hydrogen presents a unique option in that sense because it can utilize what would otherwise be curtailed electricity generation from renewables and essentially use that in combination with electrolysis to generate the hydrogen and store that energy as chemical energy. The important thing in that sort of scenario is to actually ensure that you have appropriate amounts of hydrogen storage available at scale to be able to redeploy and reuse it for various different uses in the economy. And I think it's certainly of interest here in the UK where we have a large abundance of potential hydrogen storage in geological caverns, where we might couple offshore wind-based electricity generation with geological storage in areas such as Yorkshire. But it may be less relevant for other areas where you don't necessarily see a low-cost, large-scale hydrogen store. And I think more work around this area in developing storage to the point at which it is commercially viable would be a helpful start to actually increase the uptake of hydrogen for balancing the grid.
And just to clarify the logic with storing hydrogen in caverns, is it effectively that they're just very, very big and you can store large amounts of hydrogen and you don't actually need to build the vessels? Is that why that's an attractive option? Because that does seem pretty futuristic, I'd say.
In some way, yeah. So I think we didn't actually touch on this point up until now, but what's worth noting is the hydrogen has a very low volumetric energy density compared to other energy vectors such as natural gas. So actually, to be more precise, it has approximately 1/3 of the volumetric energy density of natural gas. And what that means is that at any given condition, in terms of pressure and temperature, you will find that hydrogen needs to occupy a greater volume to be able to have the same amount of energy in place. And so what we need for hydrogen, if we're storing it as a gas, is phenomenal volumes of storage. And what a salt cavern allows you to do is to essentially have a ginormous tank inside a salt deposit, which is essentially sealed tight and doesn't allow hydrogen or any other energy vector to permeate. And then it will just keep it there for a significant amount of time while you don't need it. And then when you do need it, you can withdraw it much in the same way as you might withdraw a substance from a tank, subject to the geological conditions around there, of course. And then having this, significant volume where you're able to store hydrogen just allows you to greatly reduce the amount of cost and essentially greatly reduce that and increase its potential commercial viability when looking at enhancing its uptake.
And I would presume that we can use the learnings from the fossil fuel industry of extracting shale gas and all that sort of stuff in sort of dealing with large amounts of gas underground. Okay, so I think you mentioned that currently industry is the main user of hydrogen, and that's also a large area of potential for utilizing hydrogen to decarbonize. I know that industry makes up about 1/5 of greenhouse gas emissions currently, and it has quite diverse needs, and it's typically considered a hard to decarbonize sector. Which industries do you think hold the best potential for decarbonization with the use of hydrogen?
Hydrogen can displace quite significant uses in industry, in particular high temperature heating, where electrification may be slightly less developed compared to just burning a gas, and with adaptations that needs to be in place for that. But in terms of industrial uptake, it's quite helpful to know that currently the refining and petrochemical sector use quite a lot of hydrogen in fuel gas, in blends. So that is essentially a combination of natural gas, hydrogen, and very low quantities of higher alkane gases. And they essentially burn this as a secondary fuel to be able to meet the process demands in industry today. And there are dedicated hydrogen production facilities and industrial sites across the UK today, actually, where the hydrogen is piped around an industrial facility to be able to essentially be used in the various applications. And so I would essentially think of industry as an attractive scenario, mainly because there is operational expertise around the use of hydrogen, and there is a potential to displace a larger volume of natural gas that is currently just being used as a side product or essentially being brought into the site. And hydrogen can displace that with fairly low costs.
Right. So I'd like to shift on to another potential use that you mentioned earlier, which and that's that of transport. As far as my understanding goes, the decarbonisation of cars is unlikely to involve hydrogen, as the recent price falls in battery technology seems to be making it more and more likely that car electrification rather than I don't know what the equivalent hydrification. It seems like electrification is the answer there. If you want to push back on that, then I'd be interested to know your reasoning. But as far as I can tell, it seems to be more expensive, and the infrastructure is far less expensive than the electricity. For example, in the UK, I read something that says there's only about 6 hydrogen refueling stations in the UK. So it doesn't seem like you'd want a hydrogen car if you want to drive anywhere. I think this is a perfect microcosm of the overall theme here, with broad-scale electrification and hydrogen coming in support the electrification in deep decarbonisation. And one application I would like to talk about is using hydrogen for long-haul trucking. As far as I understand, this is an area which looks quite promising. Why is that? And yeah, do you agree with my assessment that hydrogen is unlikely for passenger cars?
Yeah, so I think it's quite important to note that both hydrogen and electricity in mobility applications are at different levels of maturity. And to be quite precise, I guess electrification has progressed to a greater extent for transport applications. We've seen a lot of companies operating in this space, and we've seen a lot of manufacturing models come to the market. And in tandem, we've seen a vast amount of recharging infrastructure being distributed across various different countries. I think in Norway, plug-in electric vehicles make up something around 30% of their overall car sales. Whereas, like you mentioned with hydrogen, there are roughly around 15 refueling stations in the UK at the moment. So the recharging infrastructure just simply isn't there for hydrogen to be used and relied on quite heavily. So I think there needs to be quite a lot of development in geographical coverage of these refueling stations before hydrogen can really see the same kind of role in the passenger vehicle side. But
that's just unlikely to happen, because I feel like economies of scale are starting to kick in with electric cars, and they're just not with hydrogen. So I don't see correct me if I'm wrong, but I just don't see a scenario where hydrogen ever catches up with the cost of electric cars. Is that fair to say?
Sure. And what I would say there is that it really depends on the decisions that are made by both investors as well as politicians on the whole. You're right in that the economies of scale has kicked in, and electrification and mobility, particularly with passenger vehicles, is likely to be the predominant solution. But in countries or in regions where you might not see a significant amount of electric infrastructure, and where access to that infrastructure might not be very cheap, you could see potential for hydrogen. But you're right, the value for hydrogen in mobility application is not really for a passenger vehicle. It's for these long-haul trucking applications where you essentially need to be able to provide a huge amount of energy for transporting goods and so on, but be able to do that in a way which allows you to refuel the infrastructure rapidly, which hydrogen allows you to do, but also operate in a way where you're able to sort of move through and cover quite significant distances in transport without having to have a need for refueling. And this is where battery applications and electrification applications fall short, because at the moment the battery technology simply isn't at a scale where you're able to meet the stresses and the demands that are posed by heavy goods vehicle transport and trucking applications. And I guess in a similar sense, we can start to look at the potential value that hydrogen might offer in public transport, in buses, in trains, and so on, for very much the same reasons. At the moment, the real sort of deal breaker is the fact that battery technologies haven't evolved to keep up pace with the needs that are imposed by these really meaty applications in heavy goods transport.
Okay, so I understand if I'm understanding your logic there, it's that it takes a long time to charge up a battery, which for something like transport, long haul trucking is, time is money. So if you have to charge your truck for an hour, that's an hour you could be driving. Whereas at the moment, or with hydrogen, you could just pour hydrogen liquid. I don't know how you do it, but you'd fill up the tank very quickly and then you're on your way. And then the second part, and probably the more important part, is the range. If you wanted to have a truck that's electrified and could go 500 miles in one go, then the mass or how heavy it's going to be it becomes prohibitive. Whereas that's probably, that might not be the case with hydrogen. And I think, just to end our conversation on transport, one area that makes me very excited is talking about the decarbonisation, aeronautical decarbonisation. So decarbonizing planes and also long distance shipping, because I know these are two areas that are viewed as challenging in decarbonization, and there's no obvious solution from electrification presents themselves for either technology. So what's the progress there with using hydrogen to decarbonize them?
Yeah, so that's really interesting, because aviation undeniably is one of the hardest sectors to decarbonize. And I guess reducing emissions from propulsion or advancements in propulsion technologies have actually sort of resulted in very little progress in the decarbonization of the sector as a whole. And what, I guess, to sort of give you an overview, there has been quite a lot of developments in electrification of aviation in essentially looking at hybrid electric flights. But these are very much at the sort of development stage, and essentially there's, very little emissions reduction expected because of the fact that it will still rely on some liquid fuel. Biofuels are quite attractive in this context because of the high energy density of biofuels, but then the concerns are all associated with the actual emissions from biofuels themselves and the limited availability. But I guess in the hydrogen space, there's been quite a lot of work in thinking about using liquefied hydrogen for the propulsion and use, etc. But liquefying hydrogen is very expensive. The plus side is that the mass energy density is very high, although the volumetric energy density is very low. And in liquefying, you get to greatly increase the volumetric energy density of hydrogen. The type of technologies that are using hydrogen for aviation applications are still at an early stage. We're seeing pilot studies being done, and that's showing quite promising results. But you could see a combination of synthetic fuels, hydrogen, and potentially even electrification playing a role, but it's very unlikely to materialize in the sort of next 5-10 years down the line.
I hope that pilot studies pun was intentional. Thank you so much. It's been a really interesting conversation, and I really like teasing apart this idea of hydrogen as a ancillary energy source to electricity. But then the conversation podcast, we like to ask 2 bonus questions. And the first one is, if you could click your fingers and bring to maturity any technology that's currently in development or even very early concept stage that you think would speed up the energy transition most effectively, which technology would it be and why?
Nuclear fusion, without a shadow of doubt. Mainly because of the fact that the enormous opportunities it provides to the large number of technologies that could do with very cheap electricity, and do so in a clean manner.
The bonus question is to do with the fact that climate change also poses large-scale ecological disaster and mass extinctions. If you could de-extinct any animal that is currently extinct, and it doesn't have to be made extinct from climate change, which animal would you pick?
Is the dodo currently extinct?
You know it is.
Yes, then bring back the dodo.
Okay. Nixon, it's been a fantastic conversation. I've really enjoyed having you on.
Fantastic. It's been a pleasure to be with you, Mike.
Thanks for listening to Low Carbon Conversations, a podcast from the IDLES programme at Imperial College London. If you'd like to get in touch, email us at idles@imperial.ac.uk. For more information about energy research at the college, or to learn about our internationally unique Master's programme in Sustainable Energy Features, visit imperial.ac.uk/Energy Features Lab.